All right. Well, I think it's 2:30 Eastern time. So if you'd like to start, why don't you go ahead?
Thank you, Lee. Thank you, everyone, being here. My name is Zhang. I teach at the Citadel, which is a military school in Charleston, South Carolina. So this talk is based on a simulated modeling scenario 6025. The blue whales and the quills are we commonly use for teaching in the Lacta Otera model. Now, in this presentation, we will see how we engage the students to do the modeling and the simulation activities to observe the changes in the population in both species and their life cycles. And because the model is difficult to solve analytically, so we will be mostly focused on the modeling and the simulation activities and the numerical solutions and the graphical solution. Now we know that the predator prey model, you can pick different pair of predator and prey, for example, fox and rabbits. But whales and quills are my favorite because there are some interesting facts here. The blue whales are listed as endangered species. Right now, only approximately between 10,000 to 25,000 blue whale left in the world. That's only about 10% of what they once were. And then blue whale is the largest animal on Earth. Now here's a picture in figure 1, the picture of blue whale. This is a picture of krill. So they are one of the smallest animals on Earth. And the blue whales, the largest animal, eat one of the smallest animal on Earth, and almost exclusively. So about 95% of their diet is prey on the krill. They eat a very small percentage of copepods in the fish. Krill themselves, they eat phytoplankton, which is the free-floating single-celled variety that are responsible for absorbing a massive amount of carbon from the atmosphere. So if blue whale become extinct, this would be result in a marked acceleration in climate change that can cause disastrous outcome for the Earth and for people and for all the other animals too. So those are the interesting facts. That's why blue whale and krill are usually chosen to be the cases when we discuss this predator and prey models. If we assume that, first we have some assumptions. We assume that the population of the blue whale at time t is, we use BT here, and the unit is thousands. We find out that if you don't use thousands, then we will have some trouble with that when we do the numerical solutions, and then the method we use is very sensitive with the large numbers. So the population, the units in thousands. And then we use KT to represent the population density. Now, krill is very small, so we don't count them. We actually, the population is measured with its density, tons per acre. So that's the KT at time t. Then the assumptions make for this model is first, if in the absence of krill, then the population of blue whale decrease at the rate of 80% per year. Now this number is difficult to estimate based on that their 95% of the diet is krill. And so we make this assumption. This is also a modification of the from the scenario that we use. The scenario only assume 10%, so which might be not as realistic. And also, if you, so I'll show you if I have time, that if we use 10%, when we do the simulation, there's also a problem with the estimation error. Now, the presence of krill then increase the blue whale population, and then the rate of growth of the is proportional of the whale population is proportional to the product of the blue whale and the krill population, and the proportionality constant is 0.1. In the absence of the predators in the uncrowded conditions, we assume that the krill population density grows at a rate 100% per year. In the presence of the blue whales, decrease the krill population density, and the rate of decrease is proportional to the product of the population of blue whale and krill, where the constant is 0.02. So we also assume that the initial population of blue whales is 20. And earlier I mentioned the unit is 1,000, so it's 20,000. And the initial krill density is 5 tons per acre. Then, so the first activity we wanted lead the students, engage the students to build a model themselves. By answering the following questions, and then they may be able to construct this model after they answer those questions. So we first ask, what does this derivative of B with respect to T represent? And then also we ask what is unit. In other classes, other than the math modeling classes, in other math course, we usually ignore the units. But for modeling class, we are very stress the importance of the units. Sometimes I tell my students that if they just by checking the units, they sometimes can tell if they get it right or wrong. The second question is we ask what's the derivative of krill K with respect to T represent, and what is its unit. And then from the first two units now, from the first two assumptions, how can we express the derivative B with respect to T? Then the fourth question we ask the students is that from the last two assumptions, that's how can we express the derivative of the krill population with respect to T. Then also the fifth question we will ask the student that what are the equilibrium points of the system, and then if we assuming we let the x-axis represent the krill population and the y-axis represent the blue whale population. And then after this exercise, and then the students from the assumptions they make, and after those 5 questions, they should be readily come up with this system of differential equations on the blue whale and the krill population here. Now, before this class, they already had class with how to find out equilibrium points, and then analyze, classify the equilibrium points. So then, so after setting those equal to 0, the two equations equal to 0, they should be able to find out the equilibrium points for this system at those 2 points. Now plugging in the numbers, the parameters in the assumptions, then we can find out the equilibrium points, those two points. To solve this system nonlinear, it's difficult to find analytic solutions. So we focus on finding the solution that is a numerical solution using the Euler's method. And that is, we approximate the differential equation using the difference equations. So which means we will approximate the derivative with respect to t as the change in b over the interval t in a sense of the discrete time intervals. Here we assume start with delta t is equal to 1, and later we can to make sure the approximation is more accurate, we will reduce this delta t to a smaller number. In order to get them started, so we will do one iteration of finding B1 and K1, maybe on the board. Then so just plug it in, plug this formula. Now we can show them that B1 is equal to 14 and K1 is equal to 8. If there's time, then we can show the students the implicit solutions, the analytic solutions can be found like this, where the C can be determined by using the plug into the initial conditions. But again, we are more focused more on the numerical and graphic solutions and observed long-term behavior of this system. So the next modeling activity, we will ask the students to perform the numerical simulation themselves. So to do a few more iterations and then fill in this table here. Notice that the approximation errors maybe become large if you have more iterations. Now, the Euler's method is simple to use, but the approximation error accumulate, so that if you have more iterations, then the error become larger and larger. If using the Chicada's form 2 or 4 method, maybe we'll have then we'll have less approximation errors, and also the approximation error may also draw incorrect, because if it's from the your numerical approximation error cost, maybe from the numbers maybe will lead student to draw incorrect conclusions about the Krill population and the blue whale population. So this is something we should keep in mind. Now, after they do it by hand for a few iterations, then it's better to do more iterations using a computer software. And so this part is better done in a lab if they don't all have a laptop. We usually allow them to do any using any software they are comfortable with, for example, Excel or MATLAB. Sometimes there were times that because some students may still have trouble with the technology, you probably should provide them a template before the class, so they can just use the template. There were times that I provided the template using Excel, MATLAB, R, and Python. From my experience, my students still prefer using Excel, maybe because it's easier to use and there's minimum coding required. In this activity, then we ask the student to use the technology to estimate when t is equal to 6. Now find estimated B6 and K6 with this the same initial condition as before. Now this time delta T is reduced to 0.1. And then also ask them to make a chart that will plot the Krill population, which is horizontal axis versus the blue population on the y-axis of the 6 years. Next, we'll ask them to provide a chart that plot this T. Now T will be the represented by the horizontal axis versus the blue whale and the Krill population respectively. Then the third activity, third part here in this activity is to ask them to using this simulation result in their Excel spreadsheet. They observe the population, the population density of Krill and the population of blue whale, and what they see about the those two population levels, and then if one or both of them have a possibility to become extinct, and then if that is the case, then estimate how long it takes for this to happen. Now also using the observation and the results from the numerical estimation, and they ask them to classify the equilibrium points as asymptotically stable or unstable. So after this exercise, they if they get it right, they should come up with a plot. This is the first plot. That's the Krill population versus the whale population. Now notice that this because of the estimation error, then this should be closed loop, but then the estimation level could not make that happen, but it's close. This is the plot here is a plot that is a plot a time versus this both population levels, and then they can also observe that both population they reach a maximum, but there is a lag, and we'll see that address that a little bit later too. So the next activity, then we will do some sensitivity analysis. We will see that if what we have seen is because of just the particular to the initial conditions and the parameters we used earlier, or if we change this the initial condition around to see if we still have a similar conclusion about the long-term behavior of the two population levels. So then, so in each scenario here, so we can see that the initial population level is changed here. So then they will for each scenario they can just answer the previous questions, then maybe draw some conclusion about the long-term behavior. So after that, they can maybe based on what they see to draw some conclusion about the two population levels. So after the activities, then they should be able to determine that the first equilibrium point is unstable. The second one, this one is stable and is periodic, and the trajectory is periodic like this. And there are so they should be able to draw the conclusion under the assumptions of this model. Then neither species will become extinct, and then so they both fluctuate and reach maximum and minimum values, and then there is a lag when when this krill is plentiful, then whale population will have a maximum rate of increase, but will reaches maximum like here when krill population is already start to decline, and then this will continue. This is in the cyclic fashion. So then if there are time, then we can improve. We can work on improve this model, then maybe refine this model by considering more factors, or making improvement about assumptions, and then or making additional sensitivity analysis. Earlier, the activity on sensitivity analysis, we only changed the initial conditions. Now you can also change the parameters here to see what this can if the conclusion will change. So one of the suggested improvement we can do is ask students to consider what are the factors included in this model and what the factors are ignored, and then for those factors are ignored, if we consider them, now how your model will change. And second one is they can so they can write a improvement in the model, and then to overcome a simplification, and maybe give them actual credit to do more sensitivity analysis, and to see that if those changes, and if you consider other source of food or for the blue whale, now how the model is going to change, or you will consider maybe not just blue whale and krill, and then maybe human hunting the blue whale is involved too. So that can also make a refinement of this model here. So that's the reference of the is based on this with some modification, and this is the textbook I used to teach my mathematical modeling class. And I think this is also a mathematical modeling textbook, and then maybe this scenario when it was written is based on this textbook here. Now have a little bit of time here, so I will. Yeah, I just want to show you that earlier I mentioned about this. I did provide them the like this Excel template, and also a template. This is a MATLAB template if they chose to, but most of them actually just chose to use the Excel. So this is the yeah, and then they can just make changes of this whenever they change the numbers, and then so this is the parameters I used in my slide. But if using this coefficients that's provided in the scenario, then you can see that it doesn't work very well, and then it may also lead to the wrong impression. This blue whale are extinct here after those iterations become negative. So which means, but this is a result of from the Euler's method, the approximation error. But if you change it to even smaller numbers, it will be something like this, and then with those graphs. Okay, so I think it's about time, and thank you very much to attending my presentation. And I see Yan-Ping Ma is here. You were in the same workshop as me about 2 years ago. Thank you for being here. Any questions?
Yeah, if I can ask a question. Do the students ever ask about using the continuous model instead of a discrete model? Because like blue whales have a mating season once a year. So because of the discrete size and that there's a lot, births are all in the winter time or early spring. there would be this big jump.
Yeah, that's the improvement of the model that they can consider, and there are also something like the maybe human hunting the blue whale. That's actually the big cause of the blue whale population dropping, and then there are also some other factors. The climate change itself may also, I mean, the decrease of the blue whale population may cause climate change, but then the climate change can also affect the population of those species in the ocean too. Yeah, those are all considered. The continuous model, then I showed in one slide that if we have time, there is we can show them the they can obtain the implicit analytic exact solution of the two species population. Probably won't have much time. It's difficult to solve for the explicit solution for BT and KT. This is a undergraduate class. We don't go that far, and then besides, it's probably more interesting doing the modeling part and then spend the whole class to provide one solution.
Thank you. Thank you for that talk.